with some examples to see how this works in other situations. Like, I would like to look us to look at a graph and read from the graph and answer a question. And then I would like to look at something maybe slightly more sophisticated like this, in which we are asked to differentiate and also find something, a function value, of course. So let's start with the graphs. Would you like to choose 49 or 50? And let's choose. Any of the graphs? Okay, saying very good. So let's say, or let's look at q prime of 7. Look at what they say. They are giving us q of x as being the ratio of f and g. In order for us to find q prime of 7, what do we have to determine first? Exactly, q prime of x. Yes, if I don't have q prime of x, how can I determine q prime of 7? So I know that q of x is f of x over g of x. So let's determine that, and then we'll come back to the book. Okay, so that's our first step. So this is problem 50 on page 190. And we have q of x is f of x divided by g of x. And the question is asking us to find q prime of 7. Of course, we have to find q prime of x first. So we look at this ratio. So this function is a ratio of two functions, f and g. So how do I differentiate a ratio? And the answer is, if you like to use my method, use it. If you don't like to use my method, use the method from the book or any other method. So the top prime times the denominator minus the top times the denominator prime. So 1 prime times 2 minus 1 times 2 prime over 2 squared. Okay, now I know that q prime of 7 will be f prime of 7 times g of 7 minus f of 7 times g prime of 7 divided by g squared of 7. All this information can be found from the graph. So let me grab my pencil. I need a pencil. There it is. So let's do that. So we want to find, let's find first f of 7 and g of 7. Can anyone give us f of 7? 1, 2, 3, 4, 5. Is it 1, 2, 3, 4, 5, 6, 7? Yes. How much is f of 7? I think it's 1, 2, 3, 4, 5. Correct? Okay, and g of 7 is 1. So I'm going to write g of 7 is 1. And f of 7, you said it was 5. I'll come back. I will zoom out in a blink. Okay, so now we want to find f prime of 7 and g prime of 7. So this was our 7. F prime of 7, I tried to find a triangle that uses the corners of the grid. Obviously, it's a positive slope. The rise is 1, and the run is 4. So I'm going to say that f prime of 7 is 1 over 4. What about g prime of g prime of 7, I'm sorry. So here it is. I form a triangle. This is the slope. This is the line. So it is a negative slope. The rise is 2 and the run is 3. Would you agree? So this will be 1 over 4 and this one will be negative 2 over 3. Agreed? Perfect. So let's put in all the information now with 1/4. And I thought I had an eraser. Okay, we'll have to wait. I'll have to erase it some other time. Okay, good. So this is 1/4, and this is negative, we said, negative 2/3. And now we put everything together. Ready? So 1/4 times 1 minus 5 times negative 2/3 divided by 1 squared, which is 1. So this is 1/4 plus 10/3. The least common denominator is, very good, so I need a 3 here and a 4 here. So 40 plus 3 will be 43. So that is Q prime of 7. Questions? Okay, so now let's look at another problem. Please select from 44 any part of it that you would like to work with. From 44, any part of it that you would like to work with. A, B, C, D. And then we'll find H prime of 2. D it is. Very good. So that is 44 on the same page. And we are given in part D, we are given h of x as being g of x divided by 1 plus f of x. Again, they're asking us to find h prime of, I believe it's 2, yes. And they're giving us some information. I'm going to copy the information before we continue. So f of 2, they say, is negative 3. G of 2, let's say, they say it's 4. F prime of 2 is given as negative 2. G prime of 2 is given as 7. Ready? What do we need to determine first, for sure? What do we need to determine first? H prime of x. Good. It's a ratio of two functions. I'm going to have to use the quotient rule again. What is going on? Why am I out of? Okay, so h prime of x, I will copy 1 plus f of x squared in the denominator, so I'm done with that. So the top function prime, g prime of x, times the denominator, minus g of x times the denominator prime, but when I differentiate 1, I get 0, so this is f prime of x. So I have determined h prime of x. All I have to do now is plug in all those numbers. Carefully, slowly, peacefully. So h prime of 2 is g prime of 2, 1 plus f of 2 minus g of 2 times f prime of 2 over 1 plus f of 2, everything squared. And now I just have to identify those values and calculate, and we're done with this. Okay, so I copy. G prime of 2 is given as 7. 1 plus f of 2 is given as negative 3. Minus g of 2 is 4. F prime of 2 is negative 2 over 1 plus negative 3. Everything squared. And now we'll just simplify this and get the numerical result. And we can move on to something else. So obviously this is negative 2 with 7 is negative 14 multiplied by 7 is negative 14 plus 8. And this is negative 2, but negative 2 squared would be 4. So this is negative 6 divided by 4, or negative 3/2. Negative 14 plus 8, negative 6 over 4, negative 3/2. So what is this? One more time. Can anyone tell us what this represents? It's h prime of 2 negative 3/2. What does it mean? Of the tangent line to the graph of h, where x is 2 is negative 3/2. Is that clear? Yes? Yes. So negative 3/2 is the slope of the tangent line to the graph of h of x when x is 2. Or you can say it's the rate of change of that function when x is 2, the instantaneous rate of change. If h is a distance, then you will say it's the instantaneous velocity. They're all the same. Is that okay? Everyone? Questions? Okay. Let's move on. Derivatives of trig functions. Yes. So there is an I here. It's kind of squeezed in there. Sorry. Derivatives of trig functions. I always ask my students, choose one and let's prove it. Of course, I'm not going to ask you to prove it. It's up to you if you want me to prove any of those, sine or cosine. If not, I'm just going to give you the result. It's up to you. So we're looking first at f of x being sine x, and we want to find f prime. And let's say g of x equals cosine x, and we want to find g prime. And then we're going to use this to determine at least two other, the derivatives of tangent and cotangent. And we can also determine secant and cosecant. Now, if you'd like to see a proof, say yes. If you don't like to see a proof, then I'll give the answer. Yes. Okay, we want to see the proof. Okay, now we have to choose which one. So remember, we proved already using the definition. We proved the square root of x last time. We proved x squared last time. And which other function we proved? E to the x, indeed. So we have that the square root of x prime is 1/2 the square root of x. We have that x squared prime is 2x. And we have that e to the x is such a nice function, no headache whatsoever. E to the x prime is e to the x. So now we want to add to that arsenal one more. And now please choose. You want to see cosine? You want to see sine? It's up to you. Sine. Okay, so we want to see sine. So I'll come back and put in the result in a couple of minutes. So we want to determine f prime of x. And at this point, for sine, but at this point, we only have the definition of the derivative. So remember, there is only one definition of the derivative, which starts with the limit as h approaches 0 from f of x plus h, which is sine x plus h, minus sine x divided by h. There are different proofs. Your book has a different method. I have a different method. I'm sure if you ask somebody else to prove it, they'll probably come up with something slightly different. They're basically all the same. Just minor variations. Okay, so there are several identities, trig identities that we have to use here. Anyone remembers? So this is the first trig identity, sine alpha plus beta. Because I need to expand this. And no, forgive me. So no, you cannot say it's sine x plus sine h. Don't say that because it's wrong. Yes, please. So sine of a sum is sine alpha cosine beta plus sine beta cosine alpha. So sine alpha cosine beta plus sine beta cosine alpha. So we are going to use this and go back and continue. So from here, I'm going to continue here. So this is limit as h approaches 0. Can anyone dictate?
Sine x cosine y plus
Cosine h and plus,
plus
sine h cosine x and minus sine x. Perfect. Is this clear so far? Yes? Yes? Okay. Next step is to notice that these two have a common factor. And pull out that common factor. Limit as h approaches 0. So if we factor out, what will we factor out from these two?
Sine x.
Perfect. Very good. Cosine h minus 1 and plus I'm sorry?
Is that it?
That's for now. Now here's another identity that we have to look at. There are two identities that I would like to present together. We are going to use one of them. Sine squared. No, that's not the one we're going to use right now. No. Sine squared alpha divided by 2 equals 1 minus cosine alpha over 2. And the other one, because they go together, cosine squared alpha over 2 is the same thing with plus. And you can say, that's wonderful, but how are you going to use this here? Here's how I'm going to use it. This piece, which is very similar to this one after I multiply both sides by -1. So if I want to solve for this, I cross multiply and also change it because I need cosine h minus 1, not 1 minus cosine alpha.
Right.
So from here, I'm going to say, or write, that cosine h minus 1 is -2 sine squared h over 2. So I'm going to replace this piece by, after cross multiplication and also multiplying by -1, by -2 sine squared h over 2. So I go back now. Limit h approaches 0. -2 sine x sine squared h over 2 plus sine h cosine x divided by h. Okay, now I need to work on this piece using another trig identity. So that trig identity is sine alpha. Let me write the original one. Sine twice alpha equals 2 sine alpha cosine alpha. But since I have h, then this will be h over 2 and this will be h over 2. Sine h is 2 sine h over 2 cosine h over 2. Why? Because I see that if I have 2x or 2 alpha, then the arguments become alpha. If I have h, then the arguments must become h over 2. So I will replace this piece by this. And then I continue. Limit as h approaches 0, -2 sine x sine squared h over 2 plus 2 sine h over 2 cosine h over 2 times cosine x. You're not surprised that I ran out of room. I know that. I can see it in your eyes. Okay. So now all is good. We have one more step, one more identity, but we have to notice that there are two terms here and they have something in common. What do they have in common? Yes, they have a 2. So this is limit h approaches 2. Let's factor out negative 2. And sine h over 2. Before we continue, I have to ask you something that I should have asked you before we started. We are determining the limit of the difference quotient. What has to happen? For sure, always, for any function that we calculate the difference quotient from, for all terms without
H. Okay.
somehow they have to go away. And we'll see in a moment what happens. And eventually
H in the denominator should cancel.
disappear. Correct. Very good. So we're after that. So can anyone give us what is left in parentheses? We took out a negative 2. We took out a sine h over 2.
Sine X.
In order to, for simplicity, for the next step, let me not pull out the negative. Let me just say positive. I pull out 2. So let's start with this term. So 2 is out, sine h over 2 is out, so I'm left with cosine h over 2 and cosine x, and minus, bless you. 2 is out, 1 from these signs is out, and I have sine x, sine h over 2. Now, last identity. Cosine alpha plus beta is cosine alpha, cosine beta, but minus sine alpha, sine beta. I'm going to have to use this identity here and replace that by what? By what? So this is my x over 2, h over 2, and that's my,
So cosine H over 2 plus X.
yes. So this whole piece was changed into this. Okay. Almost there? There is a limit. I have to talk about this and I'll come back in a second. There is a limit that we have not discussed yet, but I want to discuss it now. And a rule together with it. This particular rule appears much later in the text, but I need it now. And why not? It's a very useful rule. So if I have to determine the limit of p of x over q of x as h, not as x, it doesn't matter, as x approaches a, and I plug in a and I get one of these two indeterminate cases. If when I replace x by a, I get either these, the infinity over infinity or 0 over 0, nothing else, no other indeterminate case, then L'Hopital rule allows us to do something that otherwise it's not allowed. So the limit as x approaches a from p of x over q of x in these two particular situations, and only if it's a limit, it allows us to do this. Notice that we are not using the quotient rule. This is not the quotient rule, because this is not a function. That the quotient rule is p prime times q minus p times q prime over q squared. But this is a limit. Only inside a limit. When we have infinity over infinity or 0 over 0, only inside a limit. When we calculate a limit and these two pop up, then we are allowed to write this. Okay, and now I want to talk about a function that is sine x over x. we don't know how to differentiate yet. So if I want to determine limit as x approaches 0 from sine x over x, we don't know how to get this. But I know it's 0 over 0. Would you agree?
Yeah.
Okay. So let's look at the graph for a moment. I'll come back and we'll use the L'Hopital's rule in a blink. I thought, oh yeah, but I didn't start it. So please put in the graphing calculator in y equals this function, sine x over x. So in y equals sine x over x. And let's go to second table. I have to adjust as always here, this computer. Okay, second table. And I want to determine this limit as x approaches 0 from either side. Let's say 0.1. Let's say negative 0.1. Let's say negative 0.0, positive 0.001. Let's say negative 0.00000001. And now look at the graph. And of course, I would like to change the viewing window. I only care about what happens right here around 0. So let's say in the viewing window between negative 2 and 2, and between negative 1 and 2. Oh, of course. What did I do? Oh, no. I'm okay. So negative 2 and 2. That's what I did. I knew it. Okay. So we see the graph around 0. As you see, there is a tiny hole in there that it's not clear. We know that the function is undefined at 0. It's sine x over x, right? So what will be the limit then? As x approaches 0, what will be the limit? How much?
Looks like 1.
Exactly 1. Exactly 1. And we'll determine this with L'Hopital's rule when we have the final answer for sine. But I want to, I know I haven't finished. I'll come back. I want you to understand that the limit of as long as all these quantities are identical and they all approach 0, this will always be the case. So here's an example before we go back to our proof. Limit as x approaches 3 from sine x minus 3 over 2x minus 3, what do you think this equals to? 1 over 2, correct? Because x approaches 3 is the same with x minus 3 approaches 0, you can move 3 to the other side. So then this quantity and this quantity and this quantity are all the same. So this limit will be 1, but there is a 2 in front here. So that's why the limit is 1/2. So coming back finally after all this discussion, we are coming back to finalize this. Where will this go when h approaches 0? Very good. So this whole thing will approach cosine x. Now, notice one thing, that this quantity is not identical with this quantity in the denominator. It's the same with h over 2 approaches 0. That's okay. H approaches 0 or h over 2 approaches 0 is the same. But these have to be the same, so I'm going to bring this down to the denominator. It's the same thing, because if I flip it, I get 2 over h. So now I would like you to tell me, where does this go? H over 2 approaches 0. This quantity is the same. This quantity is the same. This quantity is the same, and I have sine. Never. We just graphed it, right? We just graphed it, and if all these quantities are the same, the answer is 1. So finally, I'm going to ask you, what is the derivative of sine? What is it? Cosine x. That's it. But yes, I had to show you all these identities, and I had to, yes, please.
So, if we're ever doing this, do we have to show all this work, or do we just?
I'm not going to ask you to do that. I just wanted to prove one so you know where it's coming from and how we determine it. But moving forward, we will remember that sine prime is cosine. Yes, please. L'Hopital's rule is applicable for any situation in which you get 0 over 0 or infinity over infinity. In any case. Yes. And we can go back and prove any of, and I'm going to do that. I'm going to choose a limit from the previous test, from test 1. So finally, we're going to practice this in a minute. So, oops, even more. Yeah. So then we know now that f prime is cosine x, and for g of x, cosine x prime is negative sine x. So moving forward, we have to remember these. And before we continue with the tangent, cotangent, secant, cosecant, I'd like to give an example of the L'Hopital's rule because I see you're interested. Of course, you're interested because it makes our life so much easier. So we had an example. Let's take a look. So remember, it can only be applied when we have 0 over 0 or infinity over infinity. You cannot apply it in this case. The first one, 6a, it's not applicable. In 6b, it is applicable, but I cannot show it to you because we haven't discussed the chain rule yet. But maybe I can show. Yes, actually, I can show this. And I can also show this. So please choose either D or F. D, very good. So we have in D limit as x approaches infinity from 2 minus e to the x over 2 plus 5 e to the x. So I check, I plug in, and I realize that it's infinity over infinity. If it's not infinity over infinity or 0 over 0, we cannot use L'Hopital's rule. But is it infinity over infinity? Yes, it is, because e to the x approaches infinity. E to the x approaches infinity, and this is just noise. So then limit as x approaches infinity. Let's differentiate the top. When we differentiate a constant, what do we get? 0. When we differentiate negative e to the x, we get negative e to the x. When we differentiate the denominator, we get 5 e to the x. Of course, you understand why? Because 2 prime is 0, correct? And then I'm going to do this. What is the final answer? That's it. We could not do this with L'Hopital's rule in the previous chapter because we didn't know differentiation rules. In the book, as I said, it appears in chapter 4. I'm not going to wait till chapter 4. I need it now. It's a very good tool. Why wait till chapter 4? Makes no sense. Okay, any questions? So now let's determine the derivative of the tangent. This I will not use a definition of the derivative, but I know that this is sine x over cosine x prime. And I know that this is quotient, the quotient of two functions, a ratio of two functions. I have to use the quotient rule. So the top prime is cosine x times cosine x minus the top times the denominator prime, which is negative cosine x, divided by cosine squared. But the numerator is basically cosine squared plus sine squared over cosine squared x. Please do not be tempted to simplify these two. The one is a term, the other one is a factor. We cannot do that. So, but we know that sine squared plus cosine squared is very good. So 1 over cosine squared x is nothing else but secant squared. So we have to remember moving forward that tangent prime is secant squared. So let me write the rest. of the trig function derivatives. So one more time, sine prime is cosine. Cosine prime is negative sine. Tangent x prime is secant squared. Cotangent x prime is negative cosecant squared. Secant prime is secant times tangent. And cosecant prime is negative cosecant cotangent. So moving forward, we can prove any of these using differentiation rules. And moving forward, we can apply those. Please remember that limit from sine x over x. And now let's prove it, because now we can. So now let's prove that, or find that limit without graphing the function. So limit of sine x over x as x approaches 0. If this is 0 over 0 or infinity over infinity, I can use L'Hopital's rule. If it's neither, I can't. So, is it 0 over 0? Sine 0 is 0. So sine prime is cosine x, and x prime is? So the answer is? No, it's cosine 0, which is 1. So that's how we get that one, using L'Hopital's rule. Very good. Okay, so let's apply the rules, and then we look at some limits. I have to caution you. L'Hopital's rule should not replace basic methods of finding limits. Sometimes applying L'Hopital's rule makes it extremely difficult, maybe even impossible. But applying a simple rule will give you the limit very easily. Okay? So let's look on page 197. And I'll let you choose any problem from 1 through 16, and then we'll look at other types. 1 through 16, any problem? We want to look at 6. So e to theta, tangent theta minus theta. Okay? Very good. Let's say, so problem 6, again on 197. That is g of theta equals e raised to theta times tangent theta minus theta. We have to treat it as a product rule. You can distribute, but then you have two different products. It doesn't matter. So this is function 1, and this is function 2. So g prime of theta will be the first function prime, which is e to theta, times the second function, plus the first function times the second function prime. Tangent prime is secant squared, minus theta prime is 1. You can leave it as is, or you can simply factor out e to theta. Tangent theta minus plus secant square theta minus 1. No one can do anything to it anyway, so you don't have to do anything. Any questions? Any questions? Okay, so I'd like to look at a few limits. Limits with what we just discussed. And in certain situations, we will apply L'Hopital's rule. Now, please choose from 39 through 48. Okay, so we want to start with 42. Very good. On 198. So we have limit as theta approaches 0 from cosine theta minus 1, oh, there's no need for parentheses, I'm sorry, over sine theta. Okay. So let's first identify what type of limit this is, what type of indeterminate situation, or maybe not. Maybe the answer is 15. So we're done. So when you plug in 0, what do you get for the top?
Minus 1.
So you get 1 minus 1, which is very good. And when you replace 0 in the denominator, good. So why not? We have it. We know it. Why not? The top prime. Remember, only inside the limit this is allowed. I cannot stress enough. If I didn't have the limit in front, I would have had to use, and differentiate this, I would have had to use the quotient rule. But this is inside of limit, and it's the case of 0 over 0. You can never do that in a function that you differentiate. Only the function inside the limit, if it's 0 over 0 or infinity over infinity, and if it's a ratio. Because otherwise you will not get 0 over 0, infinity or infinity over infinity if it's not a 0, if it's not a ratio. Good. So the top prime is? The bottom is? Good. Where does the top go? Where does the bottom go? How much is 0 over 1?
0.
Very good.
Also be negative tangent.
Say it again.
Negative tangent.
But it doesn't matter. You have to find the limit. It's fine. So you can replace it by negative tangent theta, and when you plug in theta 0, you get 0. Yes, of course. Same thing. Very good. Okay, so now let me choose one. Yeah, I'd like to look at 48. Same page, 198. So this is limit x approaches 1 from sine x minus 1 over x squared plus x minus 2. I would like to show two different ways here. I know now L'Hopital's rule is very convenient in this situation. Let's use L'Hopital's rule. Of course, it's 0 over 0. So let's do that. But I would like also to show the other way, the other method. Okay, so then it's a ratio. It's 0 over 0 when I plug in 1. I can't show it because we don't know the chain rule yet. Yeah. So we have to wait for about 10 more minutes. I'm going to start the chain rule and then I'll come back to show you. So right now I can show you only one method, not L'Hopital's rule yet. Okay, so notice that the denominator, first of all, if x approaches 1 gives us a 0, what is a mandatory factor in the denominator? Of course, that's the factor that creates 0 in the denominator. So of course the other one is x plus 2, and the numerator stays as x sine x minus 1. And of course, this is the same with x minus 1 approaches 0. Knowing that I have the conditions fulfilled, x minus 1 approaches 0, there is an x minus 1 here, there is an x minus 1 here. I'm going to ask you, where does this go? And you will say 1. And then when x approaches 0, where does this go? 2. So the answer is 1/2. I see 45 is in red, so let's see why is it in red. So any questions on this problem? Okay, so let's look at 45. 45, we have limit as theta approaches 0 from sine theta over theta plus tangent theta. As long as the top and bottom are not products, if it's convenient, and most probably it is going to be convenient, use L'Hopital's rule. But if it's the top and bottom are products, then the situation gets complicated. So obviously it's 0 over 0. The top goes to 0 when I plug in 0 and for theta, and the bottom goes to 0 when I plug in 0 for theta. Would you agree? Okay, so it's 0 over 0. Of course, it's a ratio, so then limit theta approaches 0. Let's differentiate the top. And we get cosine theta. And let's differentiate the denominator. And we get 1 plus secant squared theta. So now, where does the top go? To 1. Excellent. Where does the denominator go? Remember, secant squared is 1 over cosine squared. So this is 1 over cosine squared. If this one goes to 1, this one goes to 1, and 1 over 1 is, and then 1 plus 1 is 2. And this was very convenient in this case. Applying L'Hopital's rule was very, very convenient. Any questions? Okay, so we know we have two major rules. One of them is the product rule, and the other one is the quotient rule. Okay. Let's move on to 3.4, the chain rule. Okay, so there are two major ideas here. One is when we raise a function to a power, and the other one is when we differentiate a function composition. So finding this derivative and finding this derivative. These are two major topics in the chain rule. Let's start with the first one. Some time ago, last week, when we differentiated x to power n, can anyone refresh our memory? What was that equal to? N, x to n minus 1. And I said, yeah, but to be exact, I should put times x prime. X is the inner, and the power is the outer function. The reason why we did not put this in is because x prime was equal to 1. That's why we didn't. But now we have to. If this quantity is anything but plain x, like a function, and you can say, but x is a function. True. But anything but the identity function, which is f of x equals x, to the nth power prime, this will have to stay. So it will be n times f to n minus 1 and times f prime. So let's look at an example right here, right now. And then we come back to the function composition in general. Okay, so let's say 2x minus 1 to the 5th power, and I want to differentiate this. What do you think this will equal to? Yes? 2x minus 1 to the, very good, times 2, which is the inner function prime. 2x minus 1 prime is 2. Excellent. Any questions? Of course, I will rearrange it and write 10, 2x minus 1 to the 4th power, and that will be the end of it. Now, the general rule, which is the function composition, not necessarily with a power, it can be anything, right, is the same idea. So f come g of x. If you remember, this represents f of what? Very good, g of x. And now we want to differentiate this and differentiate this. And let's see what happens. When we decompose a function, how do we decompose a function? We start with the, which function? With the inner, and we go out. In this case, when we differentiate, we start with the outer. So we will have f prime of g of x multiplied by g prime of x. Exactly what we did here. We differentiated the outer, which was the power, and then we differentiated the inner, which was the function. Same idea. So this is the chain rule. Let's pick a problem and work on it for a minute. So let's say yes, 23 caught my eye, and I'll show you examples, and you can choose the next. Y equals the square root of 1 plus 2e to 3x. I believe it's 3x, is it? Yes. Good. How many functions we have here? A lot. But I will, for now, I will just say, okay, I have an inner, and I have the outer, which is the square root. This is identical with saying a function raised to 1/2 prime. What will that equal to? Right. So 1 over 2, the square root of the function, multiplied by, that's it. So one more time, the square root of f prime is 1 over 2, the square root of f. If f is just plain x, I'll stop. But I can't stop because f is not plain x, so I have f prime. So then, can anyone give it a shot? Or how do I write y prime? All I have to do is just fill in the blanks. I have 1, I have to write 1 over 2, I have to write the square root of what I have here, and I have to differentiate this function up here. So 1 divided by 2, the square root of 1 plus 2e to 3x, and now I have to be careful and differentiate the inner function. So 1 prime is 0, 2 must be 2, e to 3x prime is e to 3x times the inner function. I would have stopped if this were just e to x, but it's e to 3x, and I have to differentiate 3x, which is 3. Yes, I should not simplify inside parentheses. I should write it one more time, and I will. 6e to 3x over 2, the square root of 1 plus 2e to 3x, and yes, I will simplify, and I get 3e to 3x over the square root of 1 plus 2e to 3x. And that's the final form. And now before we look at applications and how we use this, I would like you to choose any other problem. I have to show you a problem like this one, like 26. You can invent one. It doesn't matter. We don't have to choose this one. And I have to show you anything else that you would like to look at with the chain rule. Just 1 or 2 examples are not enough. Maybe you want to choose a couple, and then I'll wait for a minute for you to work on them and see what you come up with. Any preference here? Which one? 41. Very good. So we have sine squared of e to sine squared t. Are they both squared or cubed? Yeah, they're both squared. Okay, so this we picked 42 on page 205. Oh, I'm sorry, 41, sorry. 205. And here it is, f of t equals sine squared applied to e raised to sine squared. So let's identify how many functions we have here. I have the power. I have sine. I have e to a function. I have another power, and I have sine. Okay, f prime. So remember, what I'd like to tell my students is to do this. So let's differentiate sine squared of whatever. I don't care what it is. Sine squared. I bring the power down. I multiply by the sine of the whole thing times the inner function prime. So 2 times sine raised to 2 minus 1 times sine prime of the same argument. What is sine prime? Cosine of e to sine squared t. Only now I got to this. So times. Please do not put any sum or difference here. They're all products. Be very careful. So I know it's tempting. I see it a lot. So this is a product. This is a product. This is a product. There is no addition or subtraction of anything, of terms. Okay, perfect. So times. Now I reached this. Again, cover it. You have e to a function. E to a function, prime is e to that function, times the inner function prime. But this is a power on a sine. So I have to bring 2 in front. I have to subtract 1 from the power, and then differentiate sine. When I differentiate sine, I get cosine t. Any questions?